Very good morning. Today we're going to see a problem on impulse invariance transformation technique. Three types of problems will appear in exam. One is they will give us h of s. We need to convert that into h of z. That is one type. The second type is they will give us h of z. We should get h of s. And the third type is this. So in third type, they will give us specifications. They are kp, ks, omega p, omega s, as you can observe here. Using this, we need to first design analog filter, and then using the transformation, that is impulse invariant transformation technique, we need to convert that into digital transfer function. Okay, so we'll try to solve this particular problem. The problem is like this. A digital low pass Butterworth filter is required to meet the following specification. The specifications are: first one, 20 log magnitude h of j omega, where omega, see here, this is a different omega. In general, I'll use this omega for digital filter frequency representation, which indicates that it is the frequency related to digital specifications. That is equal to 0.2 pi, which will be in radians per second, greater than or equal to minus 1.9328 dB. And the second specification is magnitude h of j omega with 20 log, that is 20 log magnitude h of j omega, where omega is equal to 0.6 pi, less than or equal to minus 13.9794 dB. The filter must have maximally flat frequency response. Find h of z to meet the above specification using impulse invariance transformation. See here, they have clearly mentioned that we should design low pass filter using which technique? Butterworth filter. But finally what we need? We need digital low pass Butterworth filter. These were the specification. Okay, in other words, we should get h of z. The point here is, do we know the formulas wherein we can obtain h of z directly based on this particular specification? No. How to solve this problem then? First step is understand the specification, write that in the form of magnitude frequency response. From the magnitude frequency response, we need to find out a transfer function which is in terms of s, or analog transfer function. Then we should apply impulse invariance transformation technique to convert analog transfer function into digital transfer function. So these is the steps which we need to follow to solve type 3 problems like this. Okay, we'll try to understand the specification that has been given. See here, omega is equal to 0.2 pi for all the values greater than or equal to minus 1.9328 dB. See here, if I assume that value here, that is 0.2 pi, so obviously other value is more than that, right? So it will become, by looking into this, we can clearly say that this will be omega p and this will be omega s, because this value is more, right? So this is low pass filter representation. In the problem also they have given us low pass filter representation. So obviously this value which is lower will become omega p, other value which is more, which will become omega s. So omega p is 0.2 pi, omega s 0.6 pi. Corresponding to omega p will have one attenuation. So that will be my kp. Similarly, corresponding to omega s will have one more attenuation or gain, that will become my ks. Now, one more point which we should remember here is, they have given us digital frequency. But if you observe the formulas which we studied in Butterworth filter design, we need to know analog frequency. So how to convert digital frequency which was given here to analog frequency? So that can be achieved with help of this particular formula, that is omega, analog omega is equal to distal omega by t. Now the next question is, have they given us this t? It's not been given. So what to do then? If t is not given, assume it as 1 second. So if you assume t is equal to 1 second, then analog omega will is values for analog omega will become same as distal omega. So if not, these values will change. This point is very, very important while solving the problem. This is where you may do mistake. You will treat this as omega p, omega s, even though t is not 1 second. At that time, you will not get correct answer. Make sure that you will convert, you will first read whether the frequencies that has been given in analog or distal, try to understand, and we need frequencies in analog quantity, so that can be obtained with help of this omega is equal to, that is analog omega is equal to distal omega by t. If t is not given, assume it as 1 second. At that time only you will get the same values. Otherwise, these omega values, that is analog omega p and analog omega s values, are totally different. Now I'll use this particular formula and I'll convert distal omegas into analog omega. This is omega p, which you will get it as same, that is 0.2 pi, omega s 0.6 pi. And now you know the values of kp, ks are given, which is kp is equal to minus 1.9328 dB, ks is equal to minus 13.9794 dB. Now once we get the specification, we need to find out order of a filter. Use this formula related to Butterworth filter. Order of a filter, we will get it as 2. Once we get order, we can easily find out poles using this particular formula. SA is equal to e power j into theta k, where theta k is given by this. K will vary from 0 to this. Only in Chebyshev filter, k will vary from 1 and it will end at 2m. Find out theta naught, theta 1. Use this particular equation to find out transfer function. Okay, substitute for s naught, s1. Simplify that further. Same steps which we used in designing low pass Butterworth filter. So finally simplify, you will get it this. What does this transfer function tells us? This transfer function is corresponding to a normalized low pass Butterworth filter for order n is equal to 2. What do you mean by normalized? When omega p is equal to omega c is equal to 1 radians per second, then it is known as normalized. So this is your final answer in analog domain? No. Why? Because omega p value is not 1 radians per second, right? So what to do then? We need to use analog to analog transformation corresponding to low pass. For that, what I need? I need cutoff frequency. So use this particular formula, find out the cutoff frequency. You'll get it as 0.7261. And I know that the suitable transformation is H2 of S can be obtained from H of S provided S has been replaced by S by omega c. This is for, and this transformation will use for analog to analog low pass Butterworth filter transformations. So I'll use the same. I'll substitute for omega c. So that means to say that wherever you will find S, it has to be replaced by S by 0.7261 in this particular expression. So I'll do the same and then I'll simplify. Okay, this is how you can simplify it. So once you simplify it, you will get it like this. Again the question comes, is this your final answer? No. Why? Because now right now what we found out? We found out a transfer function for omega p, for the given values of omega p and omega s, isn't it? But what else I need to find out as per the question? I need to find out distal transfer function. Okay. So how to find out that? So you know that we have one standard formula which is given by this H of S is equal to B by S plus A whole square plus B square. If you use impulse invariant transformation technique, you will get it like this, that is e power minus at sin bt z power minus 1 whole divided by 1 minus 2 e power minus at cos bt z power minus 1 plus e power minus 2at z power minus 2. T is missing here, kindly note on that. So this is the standard one, standard expression. That means to say that if the given transfer function is in terms of h of s, so you can observe the variable s. After applying impulse invariant transformation technique, that is with help of partial fraction expansion method and by applying Z transformation, you will get it like this. Suppose if the transfer function is in this particular fashion, then we can easily write that in this particular fashion, which we observed in last class. So I'll try to match this final expression with respect to this. The reason is, if you observe this numerator, you have a constant. We have two expressions, right? One is s plus a by s plus a whole square plus b square. Other one is b by s plus a whole square plus b square. Since the term s is not here, obviously I can't relate this final expression with that, wherein I can relate this particular expression with this, that is b by s plus a whole square plus b square. So I'll try to equate the denominator, and through that I'll try to find out the values for a and b. So this, I'll write it. So this is the standard one. It can be written like this: s square plus 2as plus a square plus b square. After you expand this, now I'll compare this with this. So from this I'll get the value for a, because 2as is equal to this, that is 1.0267s. From that I'll get the value for a, but this constant is not b. Remember this is not b or b square, because it is a combination of this a square plus b square. Equate that, you know the value of a, substitute that, you'll get the value of b. The value of b is like this. So once you get this, so I'm going to express the denominator in the form of s plus a whole square plus b square. So after you do that, you'll get it like this. That is s plus a. The value of a is 0.51335 whole square plus b square. B is 0.5136 whole square. But what does the standard expression says? It should be in this form, right? b by s plus a whole square plus b square. See here, s plus a whole square plus b square. The value of b is 0.5136. But if you look here, if you carefully observe, this value is not same as this. That means to say that denominator is matching with the standard expression, but numerator is not matching, because the value of b is this, but we have something else. So if you want to use this particular formula, then in LHS you should have this value, right? Standard one. Otherwise you can't use it. As a result, I need to convert this into standard expression. So in order to convert this into standard expression, what I'm going to do is, I'm going to somehow bring b here, that is this value. How to get that? So multiply and divide by same number, so that this will get cancelled out, you will get 1, so no change. So now this particular value, now I'll simplify and keep that as it is. And if you observe this, I don't do any change with respect to denominator, which will be written as it is. So if you observe this particular one, is it in this particular form, standard form? So here b s plus a whole square plus b square. Now is this b is matching with this b? Yes, of course. Right now we have this in standard form. No, forget about this constant. Okay, we'll keep that as it is. If this is the standard expression, after applying impulse invariant transformation, I'll get this, right? Similarly, if this is the expression, can't we write that in this particular fashion, so that you can convert a transfer function which is in S domain to Z domain? Yes, of course, I did the same. So this constant, I'll keep it as it is. So compare this with this, you'll get the value of a and b. In this standard expression, substitute for a and b and then simplify it. That's it. That is now e power a t sine b t z power minus 1 minus 2 e power minus this, and then simplify this, and then substitute for this, simplify, you will get it like this. If you want to substitute for t is 1 second, you can substitute. Only thing is you need to eliminate this. Hope you have understood this problem.